All right. So the plan for today is to answer one question. And the question is, up to this point, we assume the circuit that we have only has a sine wave as a source. But what if the circuit I'm dealing with does not have a sine wave as a source? What if it has a constant source? What if it has like exponential source? What can I do? I know the phasor method that I learned can only be applied to circuits with sine waves and cosines, basically. What can I do if I have a circuit that has other types of resistors? Can I take it to like some other domain? And just like the frequency domain, can I take him to like this new domain and treat every single element that I have as a resistor? The answer is yes. And the domain that we can actually take our circuit to is a Laplace. Which in a second, I'm going to tell you this is exactly the generalization of the frequency domain that we have. Okay. So let's just see how. So the question here is there any general method that can be applied to any circuit to solve for currents or voltages? And as I just mentioned, the answer is yes, and that domain is a Laplace. So the answer is yes, and it's a Laplace transform. But how? How can we use like this Laplace transform to solve any circuits? So methodology to use Laplace. Very first thing that we need to check is to make sure the system is linear. If the circuit is linear, then we can apply this. If the circuit is not linear, we cannot apply this Laplace transform. What can we do? We have to linearize the circuit. By whatever method that we know, Taylor expansion, any method that we know, we have to linearize the circuit. Good news is whatever circuit we're dealing with in this class is linear, so we don't really have to worry about it. But in case it is not, we always got to linearize. So first step is circuit linear. If the answer is no, well, we linearize. If the answer is yes, then we know exactly like what to do. We're going to take all the sources that we have to the S domain. We're going to take all the elements that we have to the S domain, replace them by their S equivalent or the Laplace equivalent, right? Now I have a circuit in Laplace domain. I'm going to treat every element that I have as a resistor, and I use my favorite method to solve for it. Whatever method it is, mesh analysis, node analysis, source transformation, I don't know, Thevenin and Norton, any method that I want, right? The only catch here is that like I'm solving it in an S domain. So I'm going to have to like take it back to the time domain. So if the answer here is yes, I'm going to take the Laplace transform of all my sources. So convert all sources to S domain. Also, I have to convert all my elements to S domain. To convert all elements to S domain. Now I have a circuit in S domain. So I have a circuit in S domain or Laplace domain, the same as Laplace domain. Now I can treat all the elements as resistor and solve for. So treat all elements as resistors and use your favorite method to solve for currents, voltages, or anything. Keep that in mind. When we're solving for it, we're still in the S domain, right? So it is in the S domain. So I have to use the inverse of whatever transformation I used to go back to the time. So I'm going to use the Laplace inverse to convert my solution to time domain. So convert the solution to time domain. Right? So if I know how to convert all the sources to the S domain version of it, if I know how to convert all my elements into the S domain equivalent version of it, and if I know how to go backward from S domain to time domain, then I can solve any circuits. Right? So what we're going to be doing, we're going to learn about how we can transform any source that we have, any function that we have, to the S domain version of it. Basically, how we can find the Laplace transform of any function. And then we're going to learn how we can go backward in time. And then we're going to learn how to convert whatever element that we have, a capacitor, inductor, and a resistor. What are their equivalent elements in the S domain? Just like what we did before. And if you know these things, then it's like very simple. I'm going to follow down this path and I'm going to solve for whatever I need. Right? So let's start by defining how we can go from time domain to this Laplace. Right? But before that, let me introduce a function, which is a very useful function. Definition. We define function u of t to be u of t as 1 for all times that are greater than 0, and 0 for all times that are less than 0. Right? We call this function unit step function. We call it unit because the value over here is unity. A step function because if I plot it, it looks like a step. So if I plot this, it basically looks like this. This is t, this is ut. I know it is 0 for all times less than 0, and it's 1 for all times that are greater than 0. Right? What does this function remind you of? Isn't it the same as a switch? Right? So if you remember, like if you had like a circuit that had a switch for like some times greater than like some initial time, like t naught, the switch was closed and it was like operating, which is the same as this portion of the graph. And for times less than t naught, it was basically open, which is like down here, right? So this function can be thought of as a switch. This function can be thought of as a switch. Right? Again, this is a mathematical function. I can do anything I want with it. I can basically shift it. I can multiply it by some number. I can do anything I want. This is a function, right? For example, for instance, we can define ut minus t naught, which means I'm not shifted by t naught, right? So it is 1 for all times greater than or equal to t naught. It is 0 for all times less than t naught. Right? If I plot it, again, nothing changes. Basically, I grab this graph and shift it by t naught. Right? So it basically looks like this. This is t naught. It is 1 for all times after t naught, and it's 0 for whatever time I have less than t. Right? It's a function. I can do whatever I do with the function. Right? This is particularly very important for us for 2 reasons. First of all, it's a switch. Second, any function that we have, we're assuming that function is defined for some time greater than t naught. And for all the times that are less than t naught, the value of the function is 0. Right? So if I want to represent a function like that, I can use this step function. I'm going to tell you exactly how. But before that, let me define the Laplace transform. That was the whole point of it. So what is the Laplace transform? The Laplace transform. We define Laplace transform of function ft to be f of s, which is defined as follows. F of s is integral from minus infinity to plus infinity of f of t times e to the power of minus st dt. Right? This is basically a two-sided Laplace transform. You probably have seen this in dpq as 0 to infinity. That's a one-sided Laplace transform. This is a general version of a Laplace transform, right? Which is known as a two-sided. What's very important is that this equality here does not always hold. Basically, this integral might diverge, right? If it diverges, then there is no Laplace transform. So the region that this integral is the same as this function f of s is called the region of convergence of this Laplace transform. Right? That's not something that we're concerned about. But we got to always keep that in mind, that this equality only holds true. Basically, this integral is finite under some circumstances. And the circumstances is called a region of convergence. Quick remark. Keep that in mind. This s over here is a complex number. In general, this s is sigma plus I omega. Right? But if I assume the real part of this s, the sigma, is 0, what do I have? I have s equals I omega, which is something that we've assumed up to this point. So if I know f of s, by assuming the real part of s is 0, I can always get f of omega. Again, that is not always true. That is always true under some circumstances. And that circumstance is if the region of convergence has the y-axis in it. Basically, if the region of convergence has the imaginary axis in it, then I can always go from Laplace transform to the f of omega, which is a Fourier transform, and we say the Fourier transform exists. Otherwise, it doesn't exist. But the Laplace transform does exist, right? So, but up to this point, we assumed sigma is 0, and therefore S is ionic. So if I have f of S, I can always assume the real part is 0, and I get f of omega. Again, remember, this f of omega exists only under some condition. And I told you the condition. The condition is that the region of convergence must include the the imaginary axis, right? But again, we're not really concerned about when these things exist, right? We always assume all of them exist, right? But for a second, let's just assume the function that we're dealing with only has value, non-zero value, for some time greater than t naught. Okay? So in circuits, we only care about functions, function f of t, such that f of t is 0 for all times less than t naught. Right? How can I represent this function f of t that is defined for all times and not just the times that are greater than t naught? Well, we just defined a step function, right? So we know there exists a function g of t such that f of t can be written as this g of t times ut minus t. Look what's happening. If I look at this ut minus t naught, I know the value of ut minus t naught is only 1 after time, basically t naught, which gives me this g of t, which is exactly my f of t. For times less than t naught, this becomes 0, and my f of t is 0. Right? So basically, this g of t is exactly this f of t. By multiplying it by this step function, I can tell you like it's defined exactly on the entire real line. Right? And if that's the case, I can define the one-sided Laplace transform. Right? Let's just assume this t naught is 0. Or assume t naught is 0. And we define f of t to be gt times ut. What is f of s? Well, I know f of s is integral from minus infinity to infinity of f of t times e to the power of minus st dt. Right? I can break this down and write it as integral from negative infinity to 0 of f of t, which is this gt times ut times e to the power of minus st dt, plus integral from 0 to infinity of f of t, which is gt ut e to the power of minus st. Right? I just broke up this integral. Right? What is this ut? for all the t's that are between -infinity to 0. It is 0. This is 0. What is integral of 0? It's always 0. So this term over here is 0. What is this ut for all the times greater than 0? That's 1. So this is 1. So I can write this integral as integral from 0 to plus infinity of gt e to the power of minus st dt. And this is a one-sided integral, right? Again, I assume this t naught is 0. I can assume this t naught is any t naught. This number over here becomes t naught, right? So it doesn't really matter. So that is pretty good. So far, we have like some definitions. Let me just do a few examples using this definition. But I'll give you basically like a table that you can put it in your cheat sheet, so you can always use that table to go from time domain to the estimate. But it's good to know how to actually go from time domain to the estimate using the formula in case there is no basically function there. Yes.
I think the slope formula you wrote out, do those count towards like a function, or are we allowed to confuse that?
For the final exam, you can have 2 pages, so use it whatever you want. Sure, just like shrink it in one of them. But you can have like 2 pages. I'll post like information. All right. So let me do a few examples. Let's just say f of t is e to the power of minus at times ut. And the question is, what is f of s? Okay. Before me applying the formula here, let me draw this function. Tell you like what it looks like. This function looks like this. This is t, this is f of t. I know for all times less than 0, it must be 0. Right? And for all times greater than 0, it decays exponentially. So it should look like this. This is 1. So this is basically f of t. Right? Now let's just find f of s. F of s is integral from minus infinity to infinity of f of t e to the power of minus st dt, which is integral from negative infinity to infinity of e to the power of minus at times ut times e to the power of minus st dt. I can again break this integral up, write it from negative infinity to 0. I'm going to combine these 2 exponentials, so I get e to the power of minus a plus st times ut plus integral from 0 to infinity of e to the power of minus a plus st ut, right? For this interval from negative infinity to 0, ut is 0. Therefore, the whole integral here is 0. For this integral, this ut is 1. So the whole Laplace transform is integral from 0 to plus infinity, e to the power of minus a plus s t dt, which I know exactly how to integrate. That is minus 1 over s plus a. I have to evaluate it from 0 to infinity, which tells me that is 1 over s plus a. Right? So if I have f of t e to the power of minus at ut, the Laplace transform it as f of s, which is 1 over s plus a. Right? Let's do one more example. Let's just say I have f of t, which is 10 times ut minus 2 minus ut minus 3. And the question is, what is f of s? Right. Again, let me quickly plot this to see what it looks like. What is the first term? Ut minus 2. Well, I know it is 1 after 2, and it is 0 before that, right? I have this 10 multiplied by it, so this magnitude of it becomes 10, right? How about the second term? It's 10 times u t minus 3. So I know it is 10 for all times greater than t equals 3, right? Now I have to subtract the blue one from the red one, right? So if I plot it, for all the times from 0 to 2, from negative infinity to 2, what am I subtracting? I'm subtracting 0 from 0. So my function is 0. For all the times greater than 3, what am I doing? I'm subtracting 10 from 10. So again, it is a 0. The only thing I'm left with is times between 2 and 3. For times between 2 and 3, I'm subtracting 0 from 10. Therefore, I have a value over here, which is 10. So that is my function. That's a pulse, right? So if I want to find f of s, which is integral from negative infinity to infinity of f of t e to the power of minus st dt, this integral is always 0 besides times between 2 and 3, right? So this integral becomes integral from 2 to 3 of 10 e to the power of minus st dt. Remember, between 2 and 3, the value of the function is 10, right? Well, this is a very simple integral. This is 10 divided by minus s times e to the power of minus st evaluated between 2 and 3. This is negative 10 over s e to the power of minus 3s minus e to the power of minus 2s. I'm going to distribute this negative sign over here. So that is, and this s over here, that is 10 times e to the power of minus 2s divided by s minus e to the power of minus 3s. Right? So it's not that bad. I can always calculate. But let me quickly give you the table so you can actually use that table. Laplace transform. Table. Let's just say I am given this function f of t and the corresponding f of s. If the function f of t is delta t, which is a Dirac function, you don't know what it is if you're taking signals in system, you're going to see this Dirac function, this delta function, is basically the limit of a pulse when the duration of pulse approaches 0. And since the area underneath the pulse is 1, if the duration still approaches 0, you're going to still get like the same area underneath, but it's going to be shrunk down to like 1 point, and that's going to be this function. So it looks like this. We don't know exactly like what value this function has over here, but what we do know is that the area underneath this arrow is 1, right? So we know the Laplace transform of that is 1. If I have t to the power of n, the Laplace transform is n factorial over s to the power of n plus 1. We know what n factorial is, right? What is it? It's 1 times 2 times 3 all the way to n. Right? So just n factorial is 1 times 2 all the way to n. Right? If I have sine at times ut, this is a over s squared plus a squared. If I have cosine at ut, that is s over s squared plus a squared. If I have the step function, the Laplace transform of step function is 1 over s. If I have e to the power of minus at ut, the Laplace transform is 1 over s plus a. If I multiply this function by a t, it is similar to taking derivative of f of s in s domain. So if I have t e to the power of minus at ut, that is 1 over s plus a squared. In general case, if I have any function f of t, if I multiply it by t, it's the same as taking derivative of f of s with respect to s with a negative sign. And if I take derivative in time domain, in s domain, similar to multiplying it by s. So I have s times f of s minus some constant f evaluated at 0. You look at these two. When I multiplied a function by t in time domain, the Laplace transform was a derivative. But when I was taking derivative in time domain, the Laplace transform was that s multiplied by f of s. This is called like duality. So since this function is similar to this, and this function is similar to this, we can basically find the Laplace transform of each of them. And this is called duality. Right? Let me give you some more. Let's just say f of t, f of s. If I take second derivative of a function f of t, it is similar to multiplying f of s by s squared minus some s f of 0 minus f prime of 0. We can generalize this to like, derivative of order n, right? You know exactly like how to do it. That's going to be s to the power of n f of s minus s to the power of n minus 1 f of 0 and so on and so on. So we can generalize. Since we can take derivative, we should be able to integrate. And since we know integral is the inverse of derivative, when we're taking derivative, we multiply by s. When we're taking integral, we have to divide by s. So if I have 0 to t f of tau d tau, that is the same as dividing f of s by s. If I multiply any function f of t by u t minus t naught, since I'm shifting this by t naught, I have to multiply it by e to the power of minus s t naught. Laplace transform of f evaluated at t plus t naught. A very, very useful special case of this is when f of t minus t naught is multiplied by u of t minus t naught. Since I have this shift, it has to be multiplied by e to the power of minus s t naught. And then I have to compute the Laplace transform of f t plus t naught. But t over here is t minus t naught. T naught and t naught cancel. So I'm going to end up getting the Laplace transform of f of t. If I have two functions convolve, they're multiplied in the S domain, which is exactly the same as the frequency that we have. If we end up stretching or contracting like any function by some a that's positive, the Laplace transform would be 1 over a. Laplace transform evaluated at S. Right? Let's do like a few examples to see how we can actually use this table to find the Laplace transform rather than just a formula. Right? Example 1. This is basically the same example that we did. But this time we're going to use the table to find it. Right? First of all, Laplace transform is a linear transformation. So if I have two functions added to each other, I can find the Laplace transform of each and then add them up. I know the Laplace transform of u of t is 1 over s, since this one is shifted by this t naught. Therefore, I have to like multiply by e to the power of minus s t naught. In this case, it is minus 2s. So I have f of s using table. I know f of s is 10 times e to the power of minus 2s over s. Again, for this one, this is t naught. So I have to shift it by t naught. So I have minus e to the power of minus 3s divided by this, which is the same as what we actually draw. Right? There's no fun in this. This is something we did before. Let's do an example that's a little more complicated. So example. Let's just say f of t is t e to the power of minus at ut minus 4. And the question is, what is f of x? Right? It's a rather complicated function. Remember, if I have f t minus t naught times ut minus t naught, I just need to find the Laplace transform of f and multiply it by the shift. Right? But this function is not quite ft minus t naught. Right? If I look at this t times e to the power of minus at, it does not have t minus 4 in it. Right? So it is not ft minus t naught. But it's not a big deal. I can make it look like that. Right? So remember, if I have ft minus t naught times ut minus t naught, the Laplace transform of this is e to the power of minus st naught times f of s. So all I have to do is to make this function, this little t times e to the power of minus at, as a function of t minus 4. Because that's my t minus t naught. Remember, this is t naught. This is t. How do I do this? Do you agree I can write this t as t minus 4 plus 4? I'm doing nothing. I'm adding and subtracting. I'm going to do the same thing for this t on the exponent. So I have e to the power of minus a, t minus 4 plus 4. I already have u t minus 4. I don't have to do anything. Right? Now I can write it in terms of all t minus 4s. Right? So let's take this. So I can write this as t minus 4 times e to the power of minus a, t minus 4 plus 4, ut minus 4. I'm going to distribute this term. So I have plus 4 e to the power of minus a t minus 4 plus 4 u t minus 4. Right? Can do that. Do you agree I can write this term over here as e to the power of minus a times t minus 4 times e to the power of minus 4a? That's just the property of exponential. E to the a plus b is e to the a times e to the b. Right? That's the property of exponential. I can do the same thing over here as well. This is e to the power of minus a t minus 4 times e to the minus 4a. Right? So let's just rewrite it. This e to the power of minus 4a is a constant. So I can pull it out. Right? So I have e to the power of minus 4a times t minus 4 e to the power of minus a t minus 4 u t minus 4 plus this 4 is constant, so I have 4. This e to the power of minus 4a again is a constant. Then I have e to the power of minus a t minus 4 u t minus 4. Right? Now I can apply this reminder. Right? If I have reminder 2, Laplace transform of t times e to the power of minus at ut is 1 over s plus a squared. Laplace transform of e to the power of minus at ut is 1 over s plus a, which is exactly these two terms. They're just shifted by 4. If something is shifted by 4, I'll have to multiply the Laplace transform by e to the power of minus 4s. So f of s is e to the power of minus 4a is a constant, so it doesn't change anything, times this shift e to the power of minus 4s. Remember, t naught is 4, divided by s plus a to the power of 2. For this term, I have 4 times e to the power of minus 4a, that's my constant, times e to the power of minus 4s, which is my shift, divided by s plus a. So that is my Laplace transform. Right? That's fantastic. It's pretty good. But what now? I have the Laplace transform. I gotta have a way to go back to the time domain. So how do we do this? So the question here, given the Laplace transform, how do we get the inverse? Before me answering that question, let me define a couple of things. Right? Define some things that we're familiar with. We already defined them before. But as a reminder, I'm going to define them again. So definition. Assume h of s is a division of two polynomials. These are polynomials. Okay. We define the roots of a numerator, the zeros of this h of s, just like what we had before, and the roots of the denominator as our poles. We had it before, nothing new. So definition 1, roots of g1 of s are called zeros. Roots of G2 of S are called poles. On top of that, call this function h of s proper if the degree of numerator is less than the degree of denominator. We call h of s proper if degree of G1 of s is less than degree of G2 of s. Right? What if it's not? If it's not, it means the function is improper, it's not proper. So since the degree of the numerator is higher than the degree of denominator, I can divide it. I can divide two polynomials. Okay. Let me quickly give you an example. Like example 1. If I have s minus 1 divided by s squared plus 2s plus 1. This is a proper function because the degree of numerator is 1, degree of denominator is 2. So this is proper. If I have s squared plus 1 divided by s plus 1, this is not proper because the degree of the numerator is 2. The degree of denominator is 1. And since s squared plus 1 has a higher degree, I can actually divide these two. Right? So this is not proper. I'll make it proper. How do I make it proper? I actually divide them. If I divide them, this is s minus 1 plus 2 over s plus 1. If you don't believe me, find a common denominator. This is going to be s squared minus 1 plus 2. It's s squared plus 1 divided by s plus 1. I can actually divide. Right? Now we know these definitions. Let's try to find the inverse Laplace transform. So, question: if h of s is g1 of s divided by g2 of s, how do we find inverse Laplace? Step 1, we're going to make sure this h of s is proper. If it's not proper, we're going to make it proper. We're going to divide it. Step 1, make sure h of s is proper. Step 2, I'm going to break up this h of s to the functions I know. How do we usually break up division of two polynomials? How do we do this? We do like partial fraction decomposition. So break up the function h of s. To do this, we do partial fraction decomposition. How do we do partial fraction decomposition? We're going to look at the roots. We're going to see like how the roots are actually working. Depending on the roots of this h of s, we have 3 different cases. So depending on, so given poles of h of s, we have 3 different cases. Case 1, when we're looking at the poles, there is no repeated pole. All the poles are distinct. All the poles are different. there is no repeated pole. Case two, some of the poles are repeated. There are repeated poles. And the last case is when the poles are complex. So there are some complex poles. Right? For a second, let's just assume we know how to do all these three cases, right? Then I basically decompose my h of s to functions that I know. Now I can find the inverse Laplace using the table, right? Use the table to find inverse Laplace, right? So let's just see how we can do these three cases, because as soon as we know that, then we're done, right? Let's just start easy. Let's look at case one. Case one. There are no repeated poles. What this means is that I can write h of s as g1 of s divided by s minus p1 all the way to s minus p1. Right? That's what it means. All the poles are distinct, and they're p1 through pn. It turns out I can write this function as a1 divided by s minus p1 plus an divided by s minus p. All I got to do is to tell you like what these AIs are, right? Let's look at this A1 and see how we can find it. Well, the simplest way that always works is that you can find a common denominator. Since these two functions are exactly the same, you just need to like equate the numerators. That is the simplest way, right? Well, let's just have a shortcut, right? Let's have like a quick observation. If I look at this, let's just say I want to find A1. Assume we want to find A1. If I look at s minus p1 times h of s, what do I get? On the other side, I get A1, right? Plus s minus p1 times A2 divided by s minus p2, all the way to an times s minus p1 divided by s minus p. Do you agree with that? I'm just multiplying both sides by s minus p1, right? What happens if I look at the limit of s minus p1 times h of s when s approaches p1? What happens to this side? Well, a1 is a number, so it stays there. What is the limit of the second term when s approaches p1? It's 0, because the numerator is 0. So it's going to be 0. And every other term would be 0. And the only thing I'm left with is a1. Right? So I can generalize this to any AI I want, right? There's nothing specific about this a1. So to get AI corresponding to pole pi, I can look at AI as a limit when S goes to pi of S minus pi times H of S. Right? It's very, very simple. Let's do a quick example to see how we can actually do this. Example. Let's just say H of S is 2 times S plus 1 divided by S plus 2 times S plus 3. The question is, what is H of T? Right? Look at the poles. The poles are happening at -2 and -3. There is no repeated root. Therefore, I can write H of S as some constant A1 divided by S plus 2 plus A2 divided by S plus 3. Right? To find A1 and A2, I can always find a common denominator and equate these two and find it. Right? We can always do that. That method always works. Right? It doesn't matter if it's a repeated root or anything, that always works. Right? Well, let's just use the shortcut. I know A1 is the limit of S plus 2 times H of S when S goes to -2. Right? Remember, my poles are at S equals -2 and S equals -3. Right? What is S plus 2 times H of S? So it's limit S goes to -2. 2 S plus 1 times S plus 2 divided by S plus 2 times S plus 3. This and this cancel. I have 2 times S plus 1 divided by S plus 3. I have to evaluate it at -2. So it is -2 divided by 1. So it's -2. Right? Why was I able to do that? Because H of S was proper. Right? If it wasn't proper, we couldn't do that. So let me quickly remind you. H of S is proper. Degree of numerator is 1. Degree of denominator is 2. How do I find A2? Well, A2 is limit when S goes to -3 of S plus 3 H of S. If I multiply this H of S by S plus 3, S plus 3 and S plus 3 cancel. So that's limit S goes to -3, 2 times S plus 1 divided by S plus 2. If I plot -3 over here, I have -4 divided by -1. So it's 4. Therefore, my H of S is -2 divided by S plus 2 plus 4 divided by S plus 3. Right? Does that make sense how I got this H of S? Everybody with me? Yeah? All I got to do is determine what the poles are and remove those poles. And then evaluate it at that point. Right? Now I have this H of S. I'm going to go back to my table. I know 1 over S plus A is e to the power of minus AT UT. So this function over here has H of T, which is -2 e to the power of minus 2t UT plus 4 e to the power of minus 3t UT. Right? So this is not bad. What if I have repeated roots? So case 2. We have repeated roots. Obviously, I cannot do what I did over here. right? Because if I break it down, then I'm gonna have like s minus p and s minus p to the power 2, s minus p to the power 3, and whatever the multiplicity is. So I'm not going to be able to do what I did over. Right? So let me explain how we can do it using an example. So let's just assume I have f of s, which is s plus 6 divided by s times s plus 3, s plus 2 to the power. Right? First of all, this f of s is proper. So I can do like the partial fraction decomposition. Second of all, where are my poles? Well, I know I have a pole at 0. And I have a pole at -2, which is being repeated 3 times. Right? So if I want to decompose this f of s, I have no issues with the 0. So I can write it a1 divided by s. Since this -2 is being repeated 3 times, I have to have all the multiplications of it. I have to have s plus 2. I have to have s plus 2 to the power 2. And I also have to have like s plus 2 to the power 3. Right? When I'm decomposing. So I have plus a2 divided by s plus 2 plus a3 divided by s plus 2 to the power of 2 plus a4 s plus 2 to the power. Right? Obviously, if I multiply this f of s just by this s plus 2, I'm not going to be able to get this a2. Right? Because if I multiply it by s plus 2, I'm going to have like s plus 2 over here, which cancels this like squared here. So if I find the limit when s goes to -2, this one goes to infinity. So obviously that doesn't work. Right? I still can get a1, right? Because a1 is just a simple pole. So let's get a1 and get it out of the way. So I know a1 is limit of s times f of s when s approaches 0. If I do that, if I multiply everything by s over here, the first term would be a1. The second term would be a2 times s divided by s plus 2. The second one would be a3 times s divided by s plus 2 squared. A4 times s divided by s plus 2 cubed. And if I find the limit when s goes to 0, all these terms actually approach. Right? Because the numerator is 0, denominator is non-zero. Right? So I can simply find a1, which is the limit s goes to 0 of s plus 6 divided by s plus 2 to the power of 3. So it is 6 over 8. Right? Or 3 over. So a1 is not bad. I'm claiming a4 is not bad either. So let's compute a4. And a4 is limit when s goes to -2 of s plus 2 to the power of 3 f of s. If that's the case, we have a1 times s plus 2 to the power of 3 divided by s plus a2 s plus 2 to the power of 3 s plus 2 plus a3 s to the power of 2 to the power of 3 divided by s plus squared plus a4 s plus 2 to the power of 3 divided by s plus 2. Right? This and this cancel, I only get a 4 over here. If I find the limit when s goes to -2, this is 0. This is also 0 because this cube cancels this. So I'm going to have s plus 2 squared. When s goes to -2, this portion is 0. Same thing for this third term. And I know the last one is a4. So I can find limit s goes to -2 of s plus 6 divided by s, because it's multiplied by this cube, and this cube cancels this cube. So it is 4 divided by -2, which is -2. Right? These two are not that bad. I'm left with a2 and a3. I got to be able to find. Remember, the issue here is that if I multiply this by anything like s plus 2 to the power 3 or s plus 2 to the power of 1, I'm going to end up getting s plus 2 on the denominator. Right? So I have to somehow make this function look like something without this s plus 2 to the power of 2. And in this case, a2, when there is no s plus 2 on the denominator. It turns out to be able to do that, I have to look at these things. So if I look at a2 is, let's just look at a3 first because that's easier. If I look at a3 is limit when s goes to the pole. I'm trying to get rid of this s plus 2 squared. So if I look at the derivative of this s plus 2 cube f of s, what am I getting? Remember, the derivative of 1 over s plus 2 to the power of 2 is 1 over s plus 2 to the power of 3. Right? So by taking derivative of it and multiplying it by this s plus 2 to the power of 3, I'm somehow canceling that. So that derivative is accounting for that one missing value over here to make it like power of 3. Right? So if I do that, that's limit s goes to -2 dds of, well, I have to multiply the whole thing by this number, so I have s plus 6 divided by 6. Right? What is the derivative of this? Well, it's a derivative of the numerator times derivative of the denominator minus derivative of the denominator times numerator divided by derivative divided by denominator squared. So that is 1 times s minus s plus 6 times 1 divided by s. I have to evaluate that at -2. And if I do that, it is -3 over 2. Right? So remember like how it happened. I had to take one derivative to make this s plus 2 squared similar to 1 over s plus 2 cubed. What can I do with this s plus 2 to make it look s plus 2 cubed? I have to take derivative twice. Therefore, this a4 as limit s goes to -2 d squared ds squared of s plus 2 cubed times f of s. turns out you're gonna have to have some constant multiply it, which is 1/2 factorial.
C or A2.
It's A2, thank you. Right? So it has to have like this constant, like 1/2 factorial. If I do that, if I simplify it, that is basically -3/4. Now I have my function f of s, which is a1/s, which is 3/4 over s, plus a2, or is our a2, which is -3/4 over s plus 2, plus our a3, which is -3/2 s plus 2 squared, plus a4, which is -2 s plus 2, right? Reminder, t to the power of n divided by n factorial, e to the power of minus at ut has a Laplace transform of 1/s plus a to the power of n plus 1. Right? Therefore, f of t, first term is 3/4 ut. Second one is -3/4 e to the power of minus 2t ut. This one is minus 3/2 t e to the power of minus 2t ut. And the last one I'm going to use like this formula, which is -2 divided by 2 factorial, t squared e to the power of minus 2t. Remember when we were doing like differential equation? If we have like repeated roots, we had to like multiply it by t. That's exactly right here. Right? So it shows up in our calculation. Right? Case 3. Case 3 is when there is a complex pole. It turns out there is not much of a trick. If there is a complex pole, we got to do it the old-fashioned way. Find a common denominator, try to simplify it. We have to find common denominator. So what we're going to be doing next lecture, we're going to do one example on the second case, on the third case, when there is a complex pole. And then we're going to do a few more examples to just make sure that we understand all the properties of a Laplace. And then we're going to move on to the actual elements in the circle. Right? I'll see you guys Wednesday.